Glass is a liquid. I know it is. I was told so. You were told so. You were told so. Your chemistry teacher, somewhere around 10th grade, looked at you with absolute confidence and said glass is actually a liquid, a very, very slow liquid. That's why the windows in old cathedrals are thicker at the bottom. The glass has been flowing downward for hundreds of years. And you nodded. Of course you did. Because it sounds wonderful. It sounds like exactly the kind of secret that science is supposed to reveal. The stuff you see through every day, the stuff you drink from, the stuff in your eyeglasses is secretly oozing, secretly flowing, secretly alive in a way you never suspected. That's a gorgeous idea, and it's completely wrong. But don't feel bad, because the real answer is so much stranger than the myth that I almost don't blame people for preferring the wrong one. Let me start by telling you why the myth is so convincing. Because it's not stupid. It's actually based on a perfectly reasonable chain of logic. And the people who believe it are not fools. They just haven't followed the chain far enough. They stopped too early, at the part that felt satisfying, and they missed the part where things get truly wild. Here's the argument. You know what a solid is? A solid is something where the atoms are locked into a nice orderly arrangement. Think of a crystal. Think of table salt. If you could shrink yourself down to the size of an atom and walk around inside a grain of salt, you'd see something like a dance floor where everyone is standing in a grid. Sodium, chlorine, repeating in every direction. Perfectly regular, like tiles on a bathroom floor that go on forever. Every sodium atom has exactly 6 chlorine neighbors, and every chlorine atom has exactly 6 sodium neighbors, and the spacing between them is always the same. That's a crystal. That's what we mean by solid. And the atoms found their lowest energy positions, they settled in, and they stay put. They jiggle a little, sure, because of heat, because even at room temperature the atoms are vibrating like crazy, but they jiggle around fixed spots, like people shivering in a queue. They vibrate, but they don't wander. Now a liquid is the opposite. In a liquid, the atoms have no fixed spots. They roam, they slide past each other, they're disordered and free. If you shrink down inside a glass of water, you don't see a neat grid, you see a crowd at a party. Everybody's bumping around, no assigned seats, no grid, no pattern that repeats. Somebody shoves past you, somebody else drifts by. The whole thing is chaos. That's a liquid, no long-range order, no structure that persists. So the question is simple. What about glass? Where does glass fit in this picture? Well, physicists have a very powerful way to look at the arrangement of atoms in a material. You shoot X-rays at it. X-rays have wavelengths about the same size as the spacing between atoms, so they scatter off the atoms and create a pattern. And the pattern tells you how the atoms are arranged. If you shoot X-rays through a crystal, you get something beautiful. You get a very particular pattern of bright spots arranged in a grid. Sharp, precise dots. That's because the atoms are arranged in a grid, and the X-rays bounce off the planes of atoms and interfere constructively at very specific angles. It's the same physics as light bouncing off a grating, or the rainbow you see on the back of a compact disc. The Braggs, father and son, William Henry and William Lawrence, worked this out in the early 1900s, and it won them the Nobel Prize. You can read the entire crystal structure from those dots, every distance, every angle, every atom's position. But if you shoot X-rays through glass, you don't get those sharp dots. You get a blur, a smear, a fog, a broad mushy hump instead of crisp peaks. The atoms in glass are not arranged in a regular pattern. There's no crystal lattice, there's no repeating grid. The silicon and oxygen atoms in ordinary window glass are connected to each other, yes, bonded tightly, but they're connected in a tangled, irregular network. If a crystal is like a tiled floor, glass is like a cracked mosaic where all the tiles are the right shape, but none of them are lined up properly. And that right there is what a liquid looks like. If you take a snapshot of water molecules at any instant, you see exactly this kind of disorder. No pattern, a jumble. Glass looks the same way at the atomic level. So people say, well, if the atoms in glass are arranged like a liquid, then glass must be a liquid. It's just a liquid that got very, very cold and very, very thick. A frozen river that hasn't quite stopped moving. Then comes the part that seals the deal for most people. The part that turns a hypothesis into a certainty. They go to Chartres Cathedral, or Notre Dame, or some old church in England, and the tour guide points at the stained glass and says, look carefully. See how the glass is thicker at the bottom than at the top. That's because the glass has been flowing downward, very slowly, under the pull of gravity for 700 or 800 years, like honey on a cold day, but much slower. Glass is a liquid, And the cathedrals prove it. You can picture it, can't you? A sheet of glass in a cathedral window, and over the centuries, molecule by molecule, the glass creeps downward, pooling at the bottom like molasses in slow motion. The silent flow of ages, visible right there in the windows of Chartres. Physics you can see with your naked eye if you just look carefully enough. It's a beautiful image. There's just one problem. It's not true. None of it. Not one piece of that argument holds up under examination. Let me take this apart piece by piece, because honestly the demolition is almost as satisfying as the myth. First, the cathedral windows. The claim is straightforward. The glass has been flowing under gravity. Let's check whether that's physically possible. A materials scientist named Edgar Zanotto, working at the Federal University of São Carlos in Brazil, heard this story and decided to actually calculate whether it could happen. Not guess, not speculate, not go on intuition, but sit down with the actual chemical compositions and viscosity measurements and see what the numbers say. He looked up the compositions of about 350 different medieval glass samples, because medieval glass isn't the same as modern glass. It has different impurities, different proportions of silica and soda and lime. He calculated a typical viscosity for this glass at room temperature. And then he asked the question, how long would it take for this glass to flow enough under its own weight to produce a visible change in thickness? The answer was about 10 to the 23rd years. That's a 1 followed by 23 zeros. Now the age of the universe is about 14 billion years, which is roughly 10 to the 10th power. So the time it would take for cathedral glass to sag visibly at room temperature is not just longer than the age of the universe. It's not 10 times longer or 100 times longer. It's 1 trillion times longer than the age of the universe. You could wait through 1 trillion consecutive universes, each one 14 billion years long, and you still wouldn't see the glass move. That should settle it. But science is thorough. And more recently, in 2017, a team at Corning Incorporated and Penn State, led by a glass scientist named John Morrow, went even further. They didn't just calculate. They actually fabricated a piece of glass with the exact same chemical composition as the glass in the windows of Westminster Abbey, those magnificent 13th century stained glass windows. They measured the viscosity of this glass directly, and they pushed the measurements down to incredibly low flow rates, heroic measurements that took tremendous patience. What they found was startling. The earlier estimates of room temperature glass viscosity were actually off by 16 orders of magnitude. 16! The real viscosity was vastly lower than what had been assumed, so the glass actually flows much faster than people had thought. Except faster here still means the glass moves about 1 nanometer over the course of 1 billion years. 1 nanometer, that's a handful of atoms. Over 1 billion years. You'd need 1,000 billion years to move the glass a single micrometer, which is still far too small to see. You are absolutely definitively not going to notice that while sightseeing at Westminster Abbey. So where does the thickness come from? If the glass isn't flowing, why are cathedral windows thicker at the bottom? The answer has nothing to do with physics and everything to do with medieval glassmaking technology. In the 12th and 13th centuries, glassmakers couldn't make flat, uniform sheets the way we can today. They had a few different methods, and all of them produced uneven glass. One common method was the crown glass process. Here's how it works. You take a blob of molten glass on the end of a long iron blowpipe. You blow it into a hollow globe. Then, while it's still hot and pliable, you transfer it to a solid rod called a pontil. You open up the globe and you spin it rapidly. The centrifugal force flattens the globe into a big disc, maybe 5 feet across. The center of the disc, where the pontil was attached, has a thick bump called the bullseye. The edges of the disc are thick and uneven. The glass in between varies in thickness. You cut the disc into panes, and the panes are not uniform. One edge is fatter than the other. One side has ripples. Some parts are thinner, some thicker. Now you're a medieval builder, and you're fitting these panes into a lead frame in a window, high up in a cathedral wall. You've got a pane that's obviously thicker on one side. Which way do you install it? You put the thick side down, of course you do. For stability, for common sense, for the same reason you'd put the heavy end of a bookshelf on the floor, not up near the ceiling. Nobody wants a top-heavy pane of glass sitting in a lead, came 100 feet above the congregation. That's it. That's the whole explanation. Uneven manufacturing plus sensible installation equals thicker at the bottom. No flow required. No mysterious liquid behavior. Just medieval craftsmen doing their jobs. And here's the evidence that absolutely kills the flow hypothesis. If glass really flowed over centuries, then the oldest glass would show the most flow. The older the glass, the more time gravity has had to pull it down. But ancient Egyptian glass vessels, some of them well over 3,000 years old, show no sagging whatsoever. They look exactly the same as the day they were made. Same thickness everywhere, perfect symmetry, no pooling, no drooping, no thickening at the bottom. 3,000 years and nothing. If glass were truly flowing, even very slowly, the Egyptian pieces would be distorted mush by now. They're not, they're pristine, so the cathedral argument collapses entirely. We can stamp myth on it in big red letters and move on. But what about the atomic structure? That part was true, wasn't it? Glass really doesn't have a crystal structure. The atoms really are arranged in a disordered way like a liquid. So doesn't that make it some kind of liquid? Here's where things get genuinely interesting. Because the answer is no. But explaining why requires us to rethink what we mean by solid and liquid in the first place. Most of us carry around a very simple picture from school. Solid means ordered atoms, liquid means disordered atoms, and this picture works beautifully for nice cooperative materials like ice and water. Ice has a crystal structure, water doesn't, and you can see the sharp transition between them. You put ice in a warm room at 0 degrees Celsius, it melts. There's a definite temperature where it switches from one state to the other, and you can measure a specific amount of heat that gets absorbed in the process, the heat of fusion. Physicists call this a first-order phase transition. The density jumps, the entropy jumps, the whole character of the material changes discontinuously at one definite temperature. Glass doesn't do any of that. If you take a piece of glass and heat it very slowly, it doesn't suddenly become a liquid at some precise temperature. What happens is this. At low temperatures, the glass is hard and brittle. As you raise the temperature, the glass starts to soften. It becomes more and more pliable. It's like warming up a piece of hard candy. There's no moment where it clicks from solid to liquid. There's a gradual transition over a range of temperatures. This range is called the glass transition, and the temperature in the middle of it is called the glass transition temperature. Below the glass transition temperature, the atoms in glass are effectively frozen. They vibrate around their positions, they jiggle with thermal energy, but they don't rearrange, they don't flow. They're stuck, just like atoms in a crystal, except they're stuck in disorderly positions. Above the glass transition temperature, the atoms start to move around more freely. The material becomes a very thick, viscous liquid. If you keep heating it further, the viscosity drops, and the glass becomes the kind of liquid you're more used to seeing, the runny, orange, glowing stuff that a glassblower works with. But here's the crucial point. The glass transition is not a phase transition in the normal sense. There's no discontinuity, no sharp line, no jump in density or entropy. It's more like a gradual handoff from solid-like behavior to liquid-like behavior. And the exact temperature where you say it happens depends on how you define it, which depends partly on how fast you were cooling the glass in the first place. This is very strange. For a physicist, this is deeply unsettling. Because for ordinary phase transitions like melting and boiling, we have beautiful, rigorous theories. We understand them completely. We can derive them from statistical mechanics. We can predict the melting point of a crystal from the forces between atoms. It's clean. It's exact. The glass transition, not so much. And the reason is that the glass is not in equilibrium. Let me explain what that means. When water turns to ice, the system reaches thermodynamic equilibrium at the melting point. The atoms explore all possible configurations and settle into the one with the lowest free energy. At 0 degrees, the crystal wins. Below 0, crystal. Above 0, liquid. The system knows where it wants to be. But glass never reaches equilibrium. Here's what happens. You start with a liquid, and you cool it. If you cool it slowly enough, the atoms have time to shuffle around, try different arrangements, and eventually find the crystal structure, the arrangement with the lowest energy. The liquid freezes into a crystal. Now, if you cool it fast, the atoms don't have time. They're like people trying to arrange chairs in a theater while the lights are going out. As the temperature drops, the atoms are moving slower and slower, getting more sluggish, and the viscosity of the liquid is rising steeply. The atoms want to crystallize. They're trying to find their spots, but the viscosity is climbing so fast that the whole system grinds to a halt. The atoms freeze wherever they happen to be standing. No one made it to their assigned seat, but everyone stopped moving. That frozen, disordered configuration is glass, and it's not the lowest energy state. Glass has higher energy than the corresponding crystal. It's trapped, frustrated. The atoms would prefer to be in a crystal, but they can't get there from where they are, because there's a mountain range of energy barriers between the glassy state and the crystalline state, and at room temperature they don't have enough thermal energy to climb over those barriers. It's like being stuck in a valley when you know there's a deeper valley on the other side of the mountains, but you can't reach it because the peaks are too high. You're in a local minimum, not the global minimum. You're settled but not satisfied. This is what makes glass so fascinating to physicists. It's a material that is out of equilibrium permanently. It's frozen in a state that it doesn't want to be in. And nobody fully understands the physics of why and how this happens the way it does. Let me give you a feeling for what's happening here, because viscosity is the key to the whole story, and I want you to really grasp it. Viscosity is just a fancy word for how much a fluid resists flowing. Water has low viscosity. It flows easily. Pour it out of a glass and it splashes immediately. Honey has higher viscosity. Pour honey and it oozes, slowly, reluctantly. Tar has even higher viscosity. Pitch, the stuff they use to waterproof ships, has such high viscosity that it looks solid. At the University of Queensland in Australia, they set up a famous experiment in 1927. They poured heated pitch into a funnel and let it drip under gravity. The first drop fell in 1938, 11 years. The next drop took 9 years. They've been running this experiment for nearly a century, and only about 9 drops have fallen. Pitch feels solid if you hit it with a hammer. It shatters. But given enough time, it flows. Very, very slowly. But even pitch, as slow as it is, flows incomparably faster than glass. The viscosity of pitch at room temperature is maybe 10 to the 8th poise. The viscosity of window glass at room temperature is somewhere around 10 to the 30th poise, or even higher. The difference between pitch and glass is like the difference between the speed of a sprinting cheetah and the speed of a continent drifting across the Earth's surface. They're not even in the same conversation. And the way viscosity changes with temperature in a glass-forming liquid is extraordinary. If you plot it on a graph, with temperature on one axis and the logarithm of viscosity on the other, you see the most dramatic curve in all of material science. As you cool the liquid from high temperature, the viscosity starts climbing. Not linearly, not gently. It goes up and up and up, faster and faster, like a rocket taking off. Over a range of just a few hundred degrees, the viscosity can change by 15 or 20 orders of magnitude, from the viscosity of olive oil to the viscosity of a mountain. In the same material, no other physical property of any material changes by that many orders of magnitude over such a small temperature range. Nothing in physics behaves like that. The viscosity of a glass-forming liquid near the glass transition is the most dramatically changing quantity I know of, and we don't have a first principles explanation for why it does this. Oh, we can describe it. We can measure the viscosity as a function of temperature, and we can plot beautiful graphs showing how it changes. For some materials, the viscosity rises gradually as the temperature drops, like a long, steady hill. Physicists call these strong glass formers. Silicon dioxide, the main ingredient in window glass, is a strong glass former. Its viscosity changes smoothly and predictably as you cool it. It's well behaved. For other materials, the viscosity rises incredibly steeply near the glass transition, like the face of a cliff. These are called fragile glass formers, which is terribly confusing terminology, because fragile here doesn't mean the glass breaks easily. It has nothing to do with mechanical toughness. It means the viscosity changes abruptly, dramatically, near the transition. A fragile glass former is one where the viscosity goes from moderate to astronomical over a very narrow temperature range, as if the material suddenly realized it was supposed to stop flowing and slammed on the brakes. This classification, strong versus fragile, was introduced by a physical chemist named Austin Engel, and it's been enormously useful for organizing the data. But here's the thing. It's a description, not an explanation. We can measure which materials are strong and which are fragile. We can plot them on a beautiful diagram. But we don't know, from the fundamental interactions between atoms, what makes one material strong and another fragile. We don't know why silicon dioxide sits calmly on the strong side, while certain organic liquids and metallic alloys fall dramatically on the fragile side. The atoms know, we don't. And by the way, not every liquid forms a glass with equal ease. In principle, any liquid can be turned into a glass if you cool it fast enough. But some materials form glass readily, practically begging to be disordered, while others are stubborn and will crystallize no matter how fast you try to cool them. Water, for instance, is extremely reluctant to form a glass under normal conditions. You have to cool it at fantastically high rates, millions of degrees per second, to outrun crystallization. Metallic glasses require special alloy compositions and rapid quenching techniques. But silicon dioxide is a champion glass former. You can cool it at a leisurely pace, and it will form glass every time. Its tangled tetrahedral network makes crystallization difficult because the atoms have to perform a very specific, coordinated rearrangement to organize into a crystal, and it's easy for them to get stuck in a tangle instead. We have empirical formulas that fit these curves quite well. There's one called the Vogel-Fulcher-Taman equation that does a good job of describing the temperature dependence of viscosity for many glass-forming liquids. But empirical formulas are descriptions, not explanations. They tell you what happens. They don't tell you why. And there's a deeper mystery, a paradox, that has haunted glass physics since 1948. It was noticed by a chemist named Walter Kausmann, and it goes like this. When you cool a liquid below its normal melting point without letting it crystallize, you have what's called a supercooled liquid. Lots of materials can be supercooled. Honey is a supercooled sugar solution in a way. Now, as you cool a supercooled liquid further, you can measure its entropy, the amount of disorder in the system. And the entropy decreases as it cools, which makes sense. Things get more ordered as they get colder. But here's the problem. The entropy of the supercooled liquid is higher than the entropy of the crystal at the same temperature, which also makes sense, because the liquid is more disordered than the crystal. But the liquid's entropy is decreasing faster than the crystal's entropy as you cool them both. The two curves are converging, and if you draw those curves out, extrapolate them to lower temperatures, the curves cross. At some temperature, the entropy of the liquid equals the entropy of the crystal. And below that temperature, if the curves kept going, the liquid would have less entropy than the crystal, less disorder than the crystal. A liquid, which is supposed to be the disordered phase, would be more ordered than the crystal. The messy pile of clothes would be neater than the folded laundry. That's thermodynamically absurd. It violates the third law of thermodynamics. It can't happen. This is Kausmann's paradox. The temperature where the extrapolated curves cross is called the Kausmann temperature. And it's a real temperature, a finite number, not zero. Nature avoids the paradox. The glass transition always intervenes before you reach the Kausmann temperature. The liquid freezes into a glass, its dynamics shut down, and the entropy stops following that dangerous extrapolation. It's as if nature says, I am not going to let you reach that absurd conclusion. I'll freeze you first. But why? Why does the glass transition happen when it does? Is it precisely because of the approaching Kausmann temperature? Is there some deep thermodynamic reason? Or is it just kinetics, just the atoms running out of time with no deeper significance? This has been debated for decades, and the debate is still alive. Some theorists believe there's a real thermodynamic phase transition lurking underneath the glass transition, an ideal glass transition at the Kausmann temperature that we can never actually observe, because the kinetics always intervene first, like a waterfall that you can hear but can never quite reach because the path always gives out before you get there. Others say no, there's no hidden transition. The Kausmann extrapolation is just misleading. The curves don't actually cross if you account for everything properly. The apparent paradox is an artifact of naive extrapolation, like predicting that because a child is growing 2 inches a year, they'll be 8 feet tall by age 30. The growth slows down. The entropy curve bends. There's no paradox, just an incomplete model. And more recently, some researchers have tried to approach the Kausmann temperature experimentally using extraordinarily patient methods. One group studied a piece of amber that was 20 million years old, which has had an astronomical amount of time to relax toward equilibrium, far more than any laboratory glass. What they found was that the relaxation dynamics didn't match the simple predictions. The behavior deviated from what the standard theories expected. The simple picture was breaking down. This is not a settled question. This is a frontier. And I want you to sit with that discomfort for a moment because this material glass is everywhere. You're looking through it right now, probably. Your windows, your drinking glasses, the lenses in your eyeglasses, the screen on your television set. And consider fiber optics. The backbone of global telecommunications is made of glass. Hair-thin strands of silicon dioxide, purified to an almost absurd degree, so pure that if the ocean were made of this glass, you could see the bottom. Light pulses enter one end of a fiber in New York and emerge from the other end in London, having traveled thousands of miles through solid glass with barely any loss. The whole modern world of instant communication, of telephone calls crossing oceans, of data streaming from one continent to another at the speed of light, rides on glass, on this weird, disordered, non-equilibrium material that we cannot explain from first principles. Or think about Gorilla Glass, the tough, thin glass that covers the screens of modern devices. It's been chemically strengthened by ion exchange, a process where small sodium ions in the surface of the glass are replaced by larger potassium ions, which crowd the surface and put it under compression, making it extraordinarily resistant to scratching and cracking. An elegant engineering trick. But the fundamental reason glass can be strengthened this way, the reason it responds to ion exchange the way it does, connects back to the same disordered structure, the same random network, the same unsolved physics. All of it is this strange, frustrated, non-equilibrium solid. We use it every single day, and we cannot explain from fundamental principles why it exists the way it does. Let me tell you about the atoms themselves now, because there's a beautiful piece of structure here that I haven't gotten to. Ordinary window glass is mostly silicon dioxide, silicon and oxygen, the same two elements that make quartz. Quartz is a crystal, gorgeous hexagonal crystals, those pointed transparent columns you see in mineral shops. That's silicon and oxygen, arranged in a perfectly ordered lattice. Glass is also silicon and oxygen, same atoms, same chemical bonds, same forces pulling them together. But the arrangement is completely different. In quartz, every silicon atom sits at the center of a tetrahedron of 4 oxygen atoms. And these tetrahedra link up corner to corner in a regular repeating pattern that extends throughout the entire crystal. Billions upon billions of tetrahedra all in lockstep. It's like a 3-dimensional wallpaper pattern that goes on forever. Glass is different. The tetrahedra still exist. Each silicon is still bonded to 4 oxygens in the same tetrahedral arrangement. Locally, the neighborhood around each silicon atom looks almost identical to quartz, but the tetrahedra are linked at random angles. Some tilt one way, some another. The bond angles between connected tetrahedra vary instead of being perfectly uniform. The local structure, what you see in your immediate neighborhood, looks regular, but the global structure, the big picture when you step back and look at the whole thing, is utterly chaotic. There's no repeating pattern. A crystallographer named William Zachariasen described this in a landmark paper in 1932. He called it the random network model, and his key insight was that glass is not a random pile of atoms. It has short-range order, but no long-range order. Up close, everything looks organized. Zoomed out, it's pandemonium. Like a city where every house is built to code, every room has 4 walls and a door, but the streets go everywhere and nowhere, and no 2 blocks are arranged the same way. This distinction between short-range order and long-range order turns out to be fundamental. It's what separates glass from both crystals and true liquids. A crystal has both short-range and long-range order. A true liquid, a hot flowing liquid well above the melting point, has very little of either. Glass has one but not the other. It's an in-between thing, a halfway house between order and chaos. And this brings us to the question that has been hovering over this whole discussion. What makes something a solid? If you define solid as something that holds its shape, then glass is unambiguously a solid. Put a glass on a table and come back in 10,000 years. It will be there, same shape, no flow, no pooling, no sagging. But if you define solid as something whose atoms are arranged in a crystal lattice, then glass is not a solid. It doesn't have a crystal structure. Its atoms are disordered. So which definition do you use? The mechanical one based on what the material does, how it behaves, or the structural one based on how the atoms are arranged? For almost every material you encounter, both definitions agree. Ice is crystalline, and it holds its shape. Water is disordered, and it flows. But glass breaks the tie. It's structurally disordered, like a liquid, but mechanically rigid, like a solid. And this right here is why the question, is glass a solid or a liquid, never gets a clean answer. It's not that we lack information. It's not that we haven't done enough experiments. It's that the question itself is poorly formed. And it assumes that solid and liquid are the only 2 options. That every material in the universe must be assigned to one box or the other. But nature doesn't owe us that convenience. I think this is one of the most important lessons in all of physics, and it goes far beyond glass. The lesson is this: when you cannot answer a question, sometimes the problem is not that you lack data. Sometimes the problem is that you're asking the wrong question. The question, is glass a solid or a liquid, treats solid and liquid as fundamental categories of nature, but they're not. They're human inventions. They're labels we slapped on the two most common behaviors we observed, and for centuries they worked fine. But nature is under no obligation to sort itself into the categories we design. Nature does what it does, and sometimes what it does is glass. The proper answer is that glass is an amorphous solid. The word amorphous is from the Greek, meaning without form, without the regular form of a crystal. Glass is a material whose atoms are locked into fixed positions, rigid and non-flowing, but those positions don't form any repeating pattern. It's order without crystallinity. It's rigidity without regularity. Let me try to give you a picture of what this looks like, because I think it's worth the effort to really see it in your mind. Imagine you could watch the atoms. Imagine you had a magical microscope that lets you see individual silicon and oxygen atoms in a blob of molten glass at, say, 2000 degrees. At that temperature, the atoms are zooming around. The silicon atoms and oxygen atoms are bonded together in little tetrahedral units, 4 oxygens around each silicon. But those units are twisting and spinning and reforming constantly. Bonds break and reform. Atoms swap partners. The whole thing is a churning dynamic mess. That's a liquid. Now imagine you start cooling it. Slowly, the atoms lose energy. They move a little less vigorously. The tetrahedra is still rotating and rearranging, but more sluggishly. Connections last a little longer before they break. The system is getting thicker. You keep cooling. Now the atoms are really dragging. A tetrahedron might hold its orientation for millions of vibrations before something shifts. The material is like a dance floor at the end of a very long night. Everyone is still technically moving, but barely. And the spaces between people are getting tighter. It's getting harder to rearrange, because every atom is boxed in by its neighbors. And then over a narrow range of temperatures, something happens. Not suddenly, not with a click, but gradually the motion stops. The tetrahedra freeze in place, bonds stop breaking. The atoms are still vibrating. They still have thermal energy, but they can't rearrange anymore. They're trapped. The liquid has become glass. No crystals formed. Nobody found an orderly position. The atoms are in a higgledy-piggledy arrangement, like guests at a party who all fell asleep in the middle of the room. And that's where they'll stay forever, as far as we can tell, because the energy barriers separating this configuration from any significantly different one are so enormous that thermal fluctuations at room temperature will never get the atoms over those barriers. This is glass. Frozen disorder. Permanent frustration. A snapshot of a liquid that never got to finish its business. Now I want to zoom out for a moment and tell you something that I find genuinely remarkable about the history of all this. Humans have been making glass for more than 4,000 years. Some of the earliest man-made glass comes from Mesopotamia, the land between the Tigris and Euphrates rivers, modern-day Iraq. Around 2,500 years before the Common Era, they were making glass beads, small amulets, colored blue with cobalt oxide. Beautiful little objects. Before that, Stone Age people had been using obsidian, which is volcanic glass, natural glass formed when silica-rich lava cools rapidly. They chipped it into arrowheads and knife blades, prizing its sharp edges. The Egyptians were making glass vessels by about 1,500 years before the Common Era. They'd form molten glass around a clay core, building up the shape layer by layer, and then scrape out the core when the glass cooled. Tedious, painstaking work. Glass was as precious as jewels in the ancient world. Then came one of the great inventions in human history, glassblowing. It was discovered somewhere along the coast of ancient Syria or Palestine, around the 1st century before the Common Era. The idea was simple but revolutionary. Instead of building glass up slowly on a core, you dip the end of a hollow pipe into molten glass, gather a blob, and blow air through the pipe. The glass inflates into a bubble. You can shape it, stretch it, cut it, mold it. Suddenly glass could be made fast and cheap. Bottles, cups, bowls, flasks. It became the plastic of the Roman world. Ordinary people could own glass for the first time. The Venetians refined glassmaking into high art on the island of Murano, guarding their techniques like military secrets, threatening exile or death for any glassmaker who left. The British developed crown glass for windows. In 1674, George Ravenscroft invented lead glass, heavier and more brilliant, the ancestor of fine crystal. And then in the 1950s, Alistair Pilkington invented the float glass process, where you pour molten glass onto a bath of molten tin and let it spread out into a perfectly flat, perfectly uniform sheet. That's how virtually all window glass is made today. 4,000 years of making glass. Thousands of artisans and engineers and chemists, generation after generation, refining the process, experimenting with compositions, pushing the material to do new things. And yet here we are in the second half of the 20th century, and we still cannot write down from the fundamental laws of physics a complete theory that explains why glass exists, why the glass transition happens, or what determines the detailed properties of the glassy state. We can make the stuff brilliantly. We can color it, temper it, laminate it, strengthen it chemically, stretch it into fibers thinner than a human hair. We can make glass so pure that light can travel through miles and miles of it with barely any loss, which is what makes fiber optics possible. But we cannot derive its behavior from first principles the way we can for a crystal or an ideal gas. That gap between what we can do and what we understand is one of the things that keeps physics alive and honest. It's a reminder that technology can race ahead of theory. We don't always understand what we make. A great physicist, Philip Anderson, who won the Nobel Prize for his work on condensed matter, once wrote that the glass transition problem may be the deepest unsolved problem in solid-state physics. He said that in 1995, and it's still largely true. Oh, there's been progress. Computer simulations have become vastly more powerful. New experimental techniques let us probe the dynamics of glass-forming liquids in ways that Kauzmann could never have imagined. But the fundamental theory, the glass equivalent of the elegant statistical mechanics that explains crystallization, hasn't arrived yet. One of the most promising ideas that has emerged is the concept of the energy landscape. Imagine that every possible arrangement of atoms in a piece of glass corresponds to a point on a vast multidimensional landscape. The height of each point represents the energy of that configuration. A crystal sits in the deepest valley, the global minimum, the lowest possible energy. A hot liquid is like a ball rolling freely across the landscape, visiting many different configurations, hopping from valley to valley. As you cool the liquid, the ball slows down. It can no longer hop over the tall ridges. It gets confined to smaller and smaller regions of the landscape, and eventually it gets trapped in some valley that is not the deepest one, some local minimum. That's the glass. What makes this picture so powerful is that it explains why different glasses can have different properties even when they're made from the same material. Depending on how fast you cooled the liquid, the ball ended up in a different valley. A slowly cooled glass might be in a deeper valley closer to the crystal state, while a rapidly quenched glass ends up in a shallower one. The landscape is the same, but the history of how you traversed it determines where you end up. Unfortunately, this energy landscape is unimaginably complicated. For a piece of glass containing 10 to the 23rd atoms, the landscape has about 10 to the 23rd dimensions. You cannot draw it, you cannot visualize it. You can barely compute anything useful about it, even with the biggest computers we have. Navigating a landscape with that many dimensions is a mathematical problem of breathtaking difficulty, and that is, in a nutshell, why the glass transition remains unsolved. And the implications go beyond glass. Understanding the glass transition would illuminate a whole family of related problems. Protein folding, for instance. When a long chain of amino acids folds into the precise three-dimensional shape that makes a working protein, it has to navigate an enormously complicated energy landscape, full of valleys and ridges and dead ends, just like a liquid cooling toward glass. Some proteins misfold and